In the last lecture, I talked about configurational entropy and how is it connected to the atomistic description of matter, and we derived this formula S equals to minus R. So we derived this formula S equals to minus R xi and xi, and if you have different species, for example A, B, C, D, E, and you have equiatomic composition, we have found that the configurational entropy contribution increases, it becomes RLM phi. So as you can see here, when it is equiatomic, we find that the most probable macro state, it's like the most probable macro state, and with a large number of microstates, and we establish this formula. This is the most important, it's a very important formula that you will see by connecting the atomistic description with the thermodynamic description, right? By using Boltzmann's hypothesis, S equals to K ln omega. So this is one very important hypothesis. Remember that S equals to K ln omega, where omega is basically the number of configurations or number of arrangements that you can basically, it is basically the number of accessible microstates, right, for a given for the most probable macro state, right? As I told you that omega is equal to omega max is the one that will be realized by the system, and that is what will maximize the entropy, and that is exactly what in the next few slides I will show you, or in the next few slides I will show you how this can be used. This idea can be used to derive other useful quantities like energy and Helmholtz free energy and heat capacity and so on. Okay, and we will show you how this S equal to K ln omega basically gives you back this constraint that the thermodynamic equilibrium, right? The idea of thermodynamic equilibrium can also be realized. So as you saw, S equals to, so basically if it is per mole, then you use R. If it is per atom, then you use Kb. Kb is Boltzmann's constant, and R equals to Kb times N, right? That we have shown. Now you see Xj is equals to Nj by N, right? Xj equals to Nj by N. So I can write this as, so you have Xj, so you have minus Kb Nj ln Nj by N. So now how can I write this? So let us look at that. So we have done this, minus Kb N Xi ln Xi plus Xb ln Xb, or it is like Xi ln Xi. Now if I do this, it's equal to 1 to R Nj ln Nj by N. So you can see this, S equals to minus R summation of Xj ln Xj, right, which is equals to minus Kb, see, R into N, right, Kb into N, J Xj ln. Now as you can see, this is nothing but, if I take minus Kb here, if I put this, so here it is, Xj is nothing but Nj by N, and there is an N here as you can see, and ln Nj, right? So now this N and this N goes off, and what you get is basically this expression, minus Kb ln Nj summation over J equal to 1 to R, if you have R components or R species, Nj ln Nj by N. Now if you have that, then as you know, if I have that, and it is entropy is an exact differential, so I can write this as ds equals to minus Kb. Kb is a constant, right? So minus Kb d of this entire term, right, of this entire summation. So minus Kb d of this entire term, and as you know, d of this summation, I can take the d inside, right? Because all these nj's are separate, right? All the nj's are like each represents j equal to 1 to r represents different species, right? So basically I can take the d inside the summation. So that's what I've done here. If you see that here you have d of the summation of this term, and now I have taken the summation out and I have put d here, which is perfectly valid because you have n1, n2, n3, and all of these make up for n. So basically you have this relation. Why can I do that? Because n1 plus n2 plus n3 plus dot means continue the sum up to r, and that is what is going to be equal to you, right? So as you can see here, I have directly used dln. So now this ln nj by n is ln nj minus ln n. So this becomes d nj ln nj minus nj ln n, right? d nj ln nj minus nj ln n. So a little bit of algebraic manipulation again. So you will see you can write this as d of nj ln nj is nothing but dnj. So so basically this is, so let me write that. So d of nj ln nj is nothing but equals to, since it's a product rule, so ln nj dnj plus nj d ln nj, which is equals to ln nj dnj. Now remember, d ln nj is nothing but d ln nj is equals to dnj by nj, right? dnj by nj, because because why? Since d ln nj dnj equals to 1 by nj, right? So this follows, right? So now you have ln nj dnj plus nj by nj, which is equal to ln nj dnj, right? So if you see this, so you have ln nj dnj plus dnj, then you have ln n dnj minus ln n dnj, and then again you have nj by n, right? nj by n dn, right? Because dn by n, right? And nj is a constant here, right? So because nj is here, right? It's a product. So as you can see here, I have written that, so nj ln n, so one term is ln n dnj, the next term is nj remains, and ln n d ln n is nothing but dn by n, right? So that's what I have written. Now if I write that, then you can further simplify it, and you will finally see that you get something like dn minus dn that goes off, and then you have this, and you have only ln nj by n dnj. Okay, so you will have ln nj by n, which is nothing but ln xj dnj. So basically ln xj dnj or minus kb ln nj by n dnj is what you will get, right? Now remember, nj, sum of nj by n has to be 1, because this is because x1 plus x2, so right, nj by n is xj, that's all. So basically nj by n equal to the mole fraction xj, and sum of xj for all over all components j equal to 1 to r, j equal to 1 to r equal to 1, right? So that's that. So now what you get is, so you have a minus kb ln nj by n dnj, that's what you got as ds. So ds is that, right? So ds equal to, so this is what we have established now, ds equals to minus kb ln nj by n dnj. Now you assume an isolated system. Why? Because I am now going to basically look at how this extremization principle, how the thermodynamic equilibrium principles, right, work, right? Energy minimization or entropy maximization, right? ds equal to 0 basically gives you, for an isolated system, ds equal to 0 gives you the extremum value, right? And d2s less than 0 basically tells that entropy is maximized. And as we know that entropy maximum principle or energy minimum principle, right, entropy maximum principle is always valid when you are talking about total internal energy is fixed, right? It cannot change, right? That's what exactly I have written here. Total U and total N cannot change, right? U is basically if you have these different energy levels. So if you have different energy levels, like energy of level J is epsilon J, then if you have like N0, so if you have, say for example, N1 atoms of type 1 in, say, energy level epsilon 1, similarly N2 atoms of type 2, so each type is distinguishable from the other, right, of type 2 in epsilon 2 and so on, then total U is nothing but epsilon J Nj, right, where epsilon J is the energy of level J, right? So now if you have du is basically epsilon J dnj, right? It is epsilon J dnj equal to 0 since nj d epsilon J equals to 0. Why? Epsilon J is fixed, right? The energy of jth level is fixed. Energy of epsilon J, which is energy of jth level, that cannot change, right? For each level the energy is fixed. This is fixed or constant. Now if this is fixed, then nj d epsilon J has to be equal to 0, right? Now you have du equals to epsilon J dnj, which is equal to summation of epsilon J dnj, which is equal to 0, and dn equals to, so dn, which is equals to, because dn is n is basically n sum nj, so dn is nothing but sum dnj, which is again equal to sum dnj has to be equal to 0. Why? Because n is constant. Total n cannot change and total u cannot change, so this is also equal to 0, right? So now let us understand the, so as we know from our macroscopic or phenomenological thermodynamics, that for S of an isolated system at equilibrium, ds has to be equal to 0, but there are constraints here. ds equal to 0 for fixed energy. Fixed energy means, now I can write fixed energy as, if I think of fixed energy means du equal to 0 is a constraint, and also fixed mole number, right? Mole number of the species, right? How many, let R species be there, but the total mole number is constant, that cannot change. So because it's an isolated system, so we are telling dn equal to 0 and du equal to 0 are the constraints, and ds has to be also equal to 0 for the systematic equilibrium. For the isolated systematic equilibrium, ds has to be equal to 0. That's the first condition, right? The extremum condition is the first condition. So ds has to be equal to 0, but these constraints are also there. That du, the total energy is fixed. That means du equal to 0 and dn equal to 0. Now use a technique which is called a Lagrange multiplier technique. So where you are telling that ds plus with these constraint, that dn equal to 0. So this we are replacing with an alpha dn and beta du, where alpha and beta are Lagrange multipliers, and we will try to find out what are alpha and beta, right? So this is your equation. If you use the Lagrange multiplier method, you have ds plus this constraint equations are there, right? This is like a Lagrange multiplier times the first one of the constraints, right? dn equal to 0, and another Lagrange multiplier times the another constant, that is du equal to 0. Now if you write that, then basically you already know what is ds, right? You know already ds, so you are using this ds. So as you know, that is only so you have ln nj by n dnj, right? That's what the minus kb ln nj by n dnj. So this is nothing but your ds, and this is nothing but your dn, and this is nothing but your du, right? So if you have that, as you can see, all of them have a summation of j, right? And j basically tells you the different species, right? So the entire term, all these terms I can club together with this dnj, because it can be like dn1 is independent, dn2 is independent, like that. Only one dependent component, right? dn3 is independent, and such that the sum of all these different species add up to the sum of mole numbers of all these different species add up to n. So if I have this, I can write it separately like sum j, and inside sum I am writing minus kb ln. So as you can see, minus kb ln nj by n, right? That is for each j, this expression works, right? Minus kb ln nj by n plus alpha plus beta epsilon j dnj equal to 0. So now if it is, so this means, that means for each j, for each species, this equation holds, right? Minus kb, this equation holds for each species, right? So whether j is 1, j is 2, j is r, right? These are different species, right? So if that is so, then kb ln nj by n equals to alpha plus beta epsilon j, right? Alpha plus beta. So because this is minus, so I am taking it on the other side, then it become, and I rewrite, so I get kb ln nj by n equals to alpha plus beta epsilon j. So now if I write, so you can now rearrange, I can take kb this side, and if I say take kb this side, this becomes alpha by kb and beta by kb epsilon j. So nj by n, if I tell nj by n, nj is the number of mole number of species j, and the ratio of mole number of species j to the total mole number, or total number of atoms, right? Total mole number is n. So nj by n is nothing but xj, right? Which is equals to e to the power alpha by kb plus beta by kb epsilon j. But still I don't know what is alpha, what is beta, right? Now as you know that e to the power a times e to the power b is nothing but e to the power a plus b, right? And since you know that, we can write this as nj by n equals to, so what I am doing is this summation, I am separating it out. I get e to the power alpha by kb, that's one term, e to the power beta epsilon j by kb, that's another. Now you see, as you can see, that summation nj by n is equal to 1, right? So that means if I do summation of nj by n, it is equal to 1. So similarly here, the summation, so I have written I, but if whether I write I or j as the initial index, it does not really matter, right? So I can write epsilon j and I can put j if you want, if you insist, I can do that. But you can also use I, right? Whether I am using I or j, it does not matter, because it is an index. So epsilon j and here it is j equal to 1, right? To be consistent, I have used the same index, this index notation j, right? So if I use the same index j, what I get is e to the power alpha by kb times e to the power beta epsilon j by kb equal to 1 when it is summed over all the j species, right? Or we can write e to the power alpha by kb, see, it is independent of j, right? It has no j. So e to the power alpha by kb, I can take it out of the summation sign, which is basically nothing but 1 by summation. Again, I can, just for consistency, so that you do not get confused, I can use j here, write j here, right? So this is what is established, right? E to the power alpha, but still I don't know what is beta, what is alpha. But now comes here. So we define some partition function. Okay, we define some partition function, which is the number of. You will later see that is basically again the number of the probability of finding an accessible microstate. So this p, and this is sum over all I, as you can see, or all species, right? So basically again, I am using I here. So I have been using, so j or I, it does not really matter, right? So I have used I here. So summation over I equals to 1 to r e to the power beta epsilon I by kb, right? So that's the thing. So if you see, this is e to the power alpha by kb, which is 1 by p, right? So nj by n equals to e to the power alpha by kb into e to the power beta epsilon I by kb, which is basically 1 by p, because e to the power alpha by kb is 1 by p, right? According to this relation. So 1 by p e to the power beta epsilon I by kb, or beta epsilon j by kb. So if it is nj by n, so So I am using nj by n. So we have to be consistent. Left hand side and right hand side, the index, the notation, the index that we use should be the same, right? If I use j on left hand side, it should be j on the right hand side. But still I don't know beta. Now comes the interesting part. So I am using here, instead of z, I will use this partition function. I am using a notation which is basically like italicized p, right? That is your partition function, and I have defined partition function. So it's just a function of these different states of energy, right? These are all the accessible energy states. Epsilon I are the accessible, all the energy states I equals to 1 to r. You have r energy states that are available. So you have r energy states that are available, right? So this is something that we have to understand here. So when I tell epsilon j is the energy of these different levels of energy, right? You have, say, r levels, you can have any number of levels, and you have these many levels of energy, right? So if you have this partition function, okay, if you have this partition function, which is basically e to the power beta epsilon I by kb, you just think of this as, if you think of this here, so you have this equation. There is this equation, yeah, this equation. So this is the equation that I was talking about. So you have this equation where nj by n equals to e to the power alpha by kb, e to the power beta epsilon j by kb, and I am defining e to the power beta epsilon I by kb summation over I equal to 1 to r as my partition function, right? As my partition function. I will give the significance of partition function. You will soon see later the physical significance of it. So now if you see that, you have ds equals to minus kb, means I am just rewriting it, ln 1 by p e to the power beta epsilon I by kb dni. Now be very careful here, yeah. So now basically you can write this as minus kb beta epsilon I by kb, because this is a ln of 1 by p. So ln of 1 by p is minus ln p, right? And because ln of 1 is 0, and ln of e to the power beta epsilon I by kb is beta epsilon by kb itself, right? Logarithm of, if I take the natural logarithm of e to the power x is basically x, right? So basically that's what I have written. So beta epsilon I by kb, and this is dn. Now so you can see here, if I rearrange a little bit, you will see that kb cancels. So you have, and there is a dni here. Are you seeing that? So here there is a dni here. So the ds, right? ds was expressed in terms of dni. So I am using that. ds is expressed as in terms of dni. So if I do this little manipulation, what I will see is this. This is kb, and this is kb, so this gone. So basically so this becomes minus beta epsilon I dni, and then kb ln p, right? There is an ln p. So why? Because there is a minus sign here, is minus sign, so plus kb ln p summation dni, so which is basically equals to so epsilon I dni is nothing but du, right? You remember? So it is basically du, and summation dni is nothing but dn. So you see, you can write this as ds equals to minus beta du plus kb ln p, where p is the partition function, and partition function is defined as e to the power. So basically it is a summation, right? It is a summation over all the energy levels beta epsilon I by kb. Now, so you got a equation, a fundamental equation in terms of particles, right? Distribution of particles, in terms of distribution of particles in different energy levels. We have got now a microscopic description of change in entropy, right? In terms of partition function. So instead of using z, I will use p here. Okay, so ln p kb ln p dn, and ds equals to, so note that here I am using a p. I'll tell you why I'm not using z. You can, in fact, you can use z. Some people use z in books, but when we use z as the partition function, there is some other concept called ensemble that I'll come to Okay, so here I haven't yet given the concept of ensemble, but only thing that I have given is there are discrete energy levels which are occupied by particles of different kinds, right? So particles can occupy different energy levels, and the different energy levels have different discrete energies like epsilon 0, epsilon 1, epsilon 2, and based on that I have defined the partition function, right? So instead of using a ensemble averaged energy, so I'll come to what is an ensemble, microscopic ensemble. I am basically giving you this idea, but it's actually equivalent. These are all equivalent. The definitions are all equivalent is what you will see. So this, what I have established now just by doing a little bit of algebra, is that there is a microscopic fundamental equation where ds is expressed in terms of s is, so where ds again is an exact differential, and it is written in terms of du and dn, right? So s is a function of un. Remember, we haven't used v here because so this is our first approximation, so we haven't used any term that represents dv. So but all said and done, if we just use this, so this basically tells you that s is a function of u as well as n, right? And it's also has a coefficient of minus beta, and in this case it is kb ln p. Now macroscopically you know that ds equals to 1 by t du, right? We have done this several times. You can also, from the combined statement of first and second laws, you can also derive it, right? And you will see that del s del u is nothing but del u del s is t. So del u del s is t, but del s del u is 1 by t, and then del s del v is p plus p by t, and del s del n is minus mu by t, right? We can also derive it from here. So that is coming from the macroscopic description or phenomenological thermodynamic description. Now if you compare the microscopic and the macroscopic description of the microscopic form of the fundamental equation and the microscopic form, right, of these two equations, where this is also ds, this is also ds. The same ds is what we are talking about for an isolated system. Now if you can see, beta basically becomes, as you can see, minus beta is 1 by t, or beta equal to minus 1 by t. And minus mu by t is kb ln p, kb ln partition function, right? Kb ln this italicized p, so kb logarithm of the partition function, and mu is nothing but minus kbt ln, right? If minus mu by t is this, so mu becomes minus kbt ln p, right? So p is now basically becoming, as you can see here, is the partition function, that we defined is now instead of beta I am putting minus 1 by t. So this becomes minus epsilon I by kbt, right? Minus epsilon by kbt. So ni by n, that is the number of species, the mole number of species I related to the total mole number, equals to 1 by p, right? This p is partition function, e to the power minus epsilon I by kbt. Right now, since I know beta, I can also find out, we know alpha, right? We also know the partition function in terms of the energy levels, right? In terms of the discrete energy levels or discrete energies that this the particles can occupy, right? It can occupy different types of energy levels like epsilon 0, epsilon 1, epsilon 2, and so on and so forth, right? These are discrete energy levels that a particle, that the system of particles can occupy, right? So I will show you how it is connected to the ensemble definition in statistical mechanics. So now all of these things have been established. So S is minus kb ni ln ni by n, which is basically coming to be, so here again, which is basically coming to be kb ni ln ni by n, so minus kb ni ln 1 by, so this will be 1 by p. It will be 1 minus epsilon I by kbt. So if you just follow this, if you follow the derivation, you will see you have ni, and then there is epsilon I by kbt and ln p, and if you look at this, if you will see kb times ni epsilon I, epsilon ni epsilon I is u, so you have 1 by t u, and kb cancels, so 1 by t u plus kb ln Cartesian function summation of I ni, which is basically now summation again over all, if all different kinds of species, this is equal to it. So this becomes S equals to, again I am writing u by t plus kb n, and see, if n is Avogadro number, then kb n is nothing but r ln, this is right, this is, and p is basically a sum of e to the power minus epsilon I by k, where epsilon I is an energy that is accessible by the particles, right? It's a energy, and it is summed over all i's that are possible, right? These i's are the different discrete energy levels that the particles in the system can occupy. Now, as you know S as a function of u by t and all. So basically, F, as you know, is Helmholtz free energy, right? This is Helmholtz free energy. F equals to u minus ts, right? It is u minus ts. So then S is this, right? S is this. This is what we just proved, right? Now you can just express F, right? You can express F, so it is u minus t, and this is the S definition. So this becomes minus n kbt ln p, and again this p, this partition function, is very important, because partition function is basically giving you the number of accessible, the sum, the number of all the accessible microstates, right, for a given for the most probable macrostate. So as a result, p in some so this basically gives you, this partition function is now giving you the connection between, see, basically nkb is r, right, which is gas constant, and when n is Avogadro number, t is temperature, F is Helmholtz free energy. These are all phenomenological. F is phenomenological, n is phenomenological, t is also. But p is coming from the distribution of particles, right? Distribution of particles across different energy levels, right? So it is like probability of finding a microstate. So it's like, you can think of this as the probability of finding a given microstate, right? So I'll come to that. It is not exactly the probability. It is basically the sum of all the accessible microstates. So now you have df, which is minus s t minus p dv plus mu dn, right? We have done it, we have got it from previously, right? We have derived it. We have also shown that f equal to minus ts, and f is basically using the conjugate variable t, right? S instead of s, we are using the conjugate variable t, and we have also established that for there we can write df is this, right? And therefore s is nothing but minus del f del t vn, right? Vn n. So first of all, f, I got a connection now, F, which is a thermodynamic potential defined phenomenologically, right, based on u minus ts. Now we got a relation with the partition function. Similarly, I got S, right, and S again can be written as n kb ln p, right? Again, this p, don't confuse this p, so plus n kbt del ln p del t. Okay, so and then from here we can basically write, so u equals to f plus ts, right, from the definition. So we can write n, you will get that it is n kbt squared. How? Because you have f plus ts, you know the f, right, you know f, and that's what I've written, and then you have ts, right, and that we have also written, and see all places p or partition function constant, right, which basically gives you the microscopic description of particles arranged in different energy levels. So similarly, I can get del Cv, which is del u del Tv, which again I get from here. So once I know the partition function of a microscopic system, right, which contains a large number of particles, we basically get all the phenomenological or macroscopic thermodynamic quantities based on this partition function. So now it becomes very useful that now it becomes very evident that these are all connected. So in all derivations we are using discrete energy levels epsilon I that are accessible by particles, right? And that's where partition function comes. It's the sum of e to the power minus so it basically gives you some sort of a distribution, a probability distribution of finding this different accessible microstates, okay, which are occupying these discrete energy levels in a system. Now, as you know, our distribution, so this is something that we have to understand and we have established every time. So this is like you have a distribution of N1 atoms of type 1, N2 atoms of type 2 and Nr atoms of type, right? So there are say total N particles and you have N1 particles of type N, of type 1, N2 particles of type 2 and Nr particles of type R, and all of these particles are occupying discrete energy levels E epsilon I, right? And with the fixed, so remember when I am talking about this distribution of particles, we are telling that we have to describe that, okay, so this is one macrostate. So basically I am telling N1, so I am telling, for example, N1, N2, Nr, they are occupying this epsilon 1, epsilon 2 and so on. So it can be epsilon whatever, how many energy levels are there, say there are 100 energy levels. So these can occupy, so such that the total U does not change. So this basically gives you this distribution, that these many balls in this box and this many balls in this box defines a state or a macro state, right? So this is a macro state, right, for a given U or for a given volume, right? A distribution of particles across discrete energy levels with that fixed total internal energy basically defines a macrostate. This is something that we have to understand very clearly. So there are many possible microstates which correspond to this given macrostate, right? So basically exactly that's what we have established before, right? You can have like if you have four distinct balls and you have two boxes, then four balls in box number 1, box labeled as 1, and 0 balls in box labeled as 2 is a macrostate, and to achieve that there is one corresponding microstate. However, 2 balls in 1 and 2 balls in 2, that is in 2, that gives you one macrostate, but it corresponds to several microstates, right? And as the number increases, as the number of energy levels increase, as the number of particles increase, there are very large number of microstates that are possible, right, associated with N particles possessing the same energy U. However, those we have to see which macrostate is most likely, right, and which omega is the maximum. So that macrostate, for that macrostate, corresponding to that macrostate, all microstates are possible, right? You can have different microstates corresponding to a single macrostate, but the macrostate that is most likely is the one that will maximize the entropy of the system. So remember, all this is one important thing that we have to also note here, that all accessible microstates for the with the same energy, right? So all microstates are equally probable, right? Whether it is AB in first box and CD in the second box, or if it is CD in the first box and AB in the second box, they are equally probable if they are microstates corresponding to a macrostate with a fixed, so corresponding to a given macrostate. Now here the given macrostate is quantified by what? By a fixed total internal energy, right? So once I have fixed the energy U, then I have told that this is the total number of particles N, and now there are various ways by which N1 particles can occupy epsilon 1, N2 particles can occupy epsilon 2, and so on, right? So the total number of microstates, so basically will describe the, so if you have the maximum number of microstates, will be the most probable, will give you the, so if you know the total number of microstates, so total number of microstates can be very large, right? If you have say R energy levels, and you have say n particles, then the total number of microstates possible are generally r to the power n, right? Where we are telling that all particles can, any particle can occupy any of the energy levels, right? That are available, right? Now see, if the total number of microstates is very large, but the most probable macrostate will have the greatest number of microstates. So there can be different states of a system that is defining the macrostate. So for each macrostate there will be some number of microstates. Now that macrostate which has the maximum number of microstates is the one which will determine the entropy of the system. That macrostate that will have the maximum number of microstates is the one, or is that which will determine the entropy of the system, and that is Boltzmann's hypothesis, right? So that's why he wrote that S equals to KBln omega, right? So this omega, now if you see, somewhere it is written as omega, and some books also write it as ZMC, where MC is called a microcanonical, MC corresponds to a microcanonical ensemble. Now you will see what does this mean, right? So I will come to that. So it is only thing, this omega or ZMC that you have, this is the partition function for a microcanonical ensemble. The physical meaning is that the omega or ZMC, whatever name you give it, it is basically giving you the total number of accessible microstates, because omega corresponds to omega max, right? That is the one which is most likely. Now this ZMC or omega, right? So this is the same, right? ZMC is same as omega, and that basically gives the total number of accessible microstates. Why I am using these two notations? Because there have been because if you look at a statistical mechanics book, then most of the times they will use this notation of Z, okay, instead of omega. Okay, so as a result, I just to give parity, I am telling that whatever different notations are used, I am using both, and I am just telling that this is the same, right? But here this MC stands for microcanonical ensemble. So what does this mean? I will just come. So what is macroscopic thermodynamic property? This is also we have to understand. There is the average of properties over all temporal microstates of the system for a given macrostate. So macrostate and state are the same, right? We have talked about that. So average of the property. So you have, but one macrostate corresponds to a huge number of microstates, right? And each of these microstates can appear at some instant of time, right? So this if I take this temporal distribution of all the microstates, and for each microstate I have a property, and I take an average of that property, and that average is going to give me the value of the macroscopic thermodynamic property, right? That's the idea. So see, this is another thing. When we look at the statistical thermodynamics, we are talking about number of particles that is very, very large, right? Very large. So so if the number of particles is very large, number of identical systems which have the same set of thermodynamic parameters, which can be number of moles, or volume, or temperature, or pressure, or some or fixed chemical potential, or internal energy, that also will be very large. So basically, if the number of particles is large, number of identical systems, basically identical in terms of the macroscopic thermodynamic properties. So identical system or identical systems to state. So if the number of particles is very large, then the identical systems or identical systems that will have the same set of thermodynamic properties will be very large, and this collection of large number of identical systems is called an ensemble, right? So it is basically given by Gibbs. The definition is given by Gibbs. So collection of a large number of identical systems which have the same set of thermodynamic parameters, respect the same set of thermodynamic parameters, this collection of large number of identical particle systems is called an ensemble. So one of the ensembles that we have talked about, and the easiest ensembles that we talked about, means easiest to understand, is the one which is microcanonical ensemble, where microcanonical, right? So this is the MC that we talked about, right? So we define something called ZMC, which is nothing but, right? So this microcanonical ensemble tells you what? It tells you isolated. So it is basically an isolated simple system with constant internal energy U and constant volume V and constant number of particles n. So it is, so a microcanonical ensemble points to an isolated simple system with a constant energy U, constant volume V, and constant mole number, a constant number of particles n, right? So what can fluctuate? U cannot, U is fixed, V is fixed, and n is fixed. So basically T can fluctuate, pressure can fluctuate, chemical potential can fluctuate in each system as well as from system to system, right? From one system to the other, chemical potential can fluctuate, pressure can fluctuate, temperature can fluctuate, right? So this microchemical ensemble is characterized by the partition function ZMC, which is nothing but omega in Boltzmann's hypothesis, right? KBL and omega. Now canonical ensemble. Canonical ensemble is where we fix the temperature. So a collection of closed simple systems. Remember, here it was a collection, it's an isolated system, right? Cannot exchange energy or matter with the surroundings, right? Energy exchange is also not permitted. But here we are talking about fixing the temperature, then immediately we are talking about a reservoir, right? So there is a reservoir. So what we are telling is canonical ensemble is the one in which a collection of closed simple systems bounded by a thermal reservoir at constant temperature T, right? It is bounded, it has to be bounded by a thermal reservoir at constant temperature T, constant volume V, and constant mole number of particles N. But you see here the internal energy, the pressure or chemical potential, they can vary in each system and from system to system. So mu can vary, P can vary, U can vary, but T cannot, because T, it is in the system is in contact, it's a closed system in contact with the thermal reservoir, right? So this is what is called a canonical. And then you have the special type of ensembles which are used for determining many times to determine phase diagrams. So these are called grand canonical ensembles. So grand canonical ensembles are one. Those are open system, simple systems. That means mass transfer is permitted. That means particles can come in, the number of particles can increase or decrease, right? These are the variable parameters, U, P, as well as N. But what is fixed is mu. See, it's having a thermal reservoir as well as a chemical reservoir. Chemical reservoir means it will have the same chemical potential as the system, right? So fixed chemical potential, fixed volume, and fixed temperature. But U can vary, P can vary, and N can vary, and this becomes very, very interesting and important when you have multi-component system, because I can fix the chemical potential and I see that how many particles are getting, how the particles are getting distributed, and based on that particle distribution of different particles of different species, how they are distributed, we can basically arrive at phase diagrams, okay, or phase stability diagrams in multi-component systems. So there is also this, so as I told you, so this, each of these have a, we define some partition function to characterize these ensembles, right? I'm going I'm going to go very fast here, because I do not want to spend a lot of time here. What I have established here is that with this partition function known, okay, which basically gives you some sort of the total number of accessible microstates, right? So in the microcanonical ensemble, it is the total number of accessible microstates with the same energy U, same volume V, and same number of particles N, right? So if I fix the energy, if I fix the volume, and if I fix the mole number, then the number of accessible microstates is given by ZMC, right? That's the partition function. And as I told you, once you define this partition function, you can, by the way, the partition function that we defined, that P is a partition, you will soon see that this very similar to the partition function that is used for canonical ensembles, right? So ZMC is omega, which is microcanonical, which is total number of accessible microstates. So omega or ZMC both give you the total number of accessible microstates which have the same energy U, same volume V, and same number of particles N. And probability of accessing this ith microstate is given by 1 by, so it's a reciprocal of the partition function. The probability is just the reciprocal of this partition function, right? So we can write S, the same thing. This is nothing but Boltzmann's hypothesis. So as you can see here, we can write, you have this ds, so the same S, and ds is 1 by TTU, P by TTU, and we have already done that, we have established this. So basically now we can basically write everything in terms of the ZMC or partition function, and that partition function gives you the connection between the particle or atomistic description of matter and the phenomenological description of matter, which is basically given by the macroscopic thermodynamic parameters. Okay, so similarly we can do this canonical ensemble. So as you can see, you talked about, just before that we talked about P, right? What we told is P is where epsilon I is the energy of the ith energy level, right? Here also we are talking about, these are nothing but the energy of microstate, right? So this is like, these are basically equivalent, right? They are basically equivalent. Only thing I just want to tell you that the same thing basically. However, this Ui is energy of microstate I. Okay, that microstate has a collection of particles, and these particles are. So basically, instead of talking about a single different energy levels, what I am talking about is like, you have Ui is the energy of microstate I, which can have, say, N1 particles in which can have some particles in energy level epsilon 1 and energy level epsilon 2, some other particles. So basically, Ui and epsilon I are basically one and the same, right? They are basically one and the same. And now, if you have that, then the probability of finding the ith microstate is basically given by this, right? It is minus beta Ui by Z. Right, and you can basically write U as del ln ZC del beta, right? So and beta is 1 by kBT. So you can see that, we can go through that. I am not going to discuss all of this in detail, but what I am trying to say is that once you have this established, you get back, you can basically go from particle based description to the macroscopic description and come back from there. So that is possible. So we have this very special ensemble, that is the grand canonical ensemble, which is also based on this grand potential, which we have not discussed previously. So grand potential, it's the same, it's one thermodynamic potential. So we go into the macroscopic thermodynamics, which is basically given by, so for example, G is H minus Ts, F is U minus Ts, right? So there are these different thermodynamic potentials that we can define, right? Where we are replacing where we are doing the Legendre transform, that A is equal to Vn, we are basically writing as F equals to some, so we are trying to replace, so U as Vn, say for example, I have U S Vn, and from there I can go to G T P N, right, where S is replaced by the conjugate variable T, and V is replaced by the conjugate variable P, right? So G is basically H minus Px, or is U plus PV, right, is free energy minus Px. Now similarly, I can write a grand potential where I am replacing N by its conjugate variable, which is mu, right? So phi is U minus Ts minus mu N, which is also given by Landau free energy omega. So this d phi is basically minus p dv minus s dt minus n d mu. So note that it is minus n d mu, okay, and where du is tds minus p dv plus mu n. So again, phi is a Legendre transform of u, where n is replaced by its slope, right, which is basically mu. Slope with respect to the, so u del n, right, del u del n, if we fix s and v, so is basically mu. So n goes to mu and s goes to t. So this is the relation that I wanted to tell you. So you have u as a function of svn, but here phi as a function of tv. So s has been replaced by t, right? So here the Legendre transform is this: s is replaced by t, and v remains v, and n is replaced by mu, right? So minus s is, now if I write in terms of grand potential, so minus s is del phi grand potential, del phi. So this phi is special, right? We have this sign. So the way we write the grand potential energy is this, right? So this is one notation. We can use different other notations. So minus and n, as you can see, it is the derivative of the grand potential energy with respect to mu, and that will give you n. And that is why it becomes very useful when it comes to understanding or evaluating or obtaining phase diagrams, right? So when we write ZZ, or this ZZ is nothing but the grand potential partition function. So grand canonical ensemble partition function, ZZ is the partition function means it's called grand canonical. You'll see that here there is minus phi, right? Instead of minus ui, you have minus phi by kBt, right here. So minus phi by kBt, and which is basically can be written as ui minus mu n by kBt, right? And where phi can be written as, again, this grand potential phi can be written as minus kBt ln z, right? So this is what I just want to talk about that. So, and as you can see, probability of appearance of a microstate I, you can write S, right? We have already established this, like S equals to minus R sum xi ln xi. So similarly, I can write minus kb pi ln pi, where pi is the probability of appearance of microstate, right? And pi isolated is basically given by 1 by zmc. Pi closed is given by e to the power minus ui by kBt by zc, right? We have established all of this. So now you have, say, a two-state system. So this is some application. So if you have two states, like two energy levels are there. So basically you have energy level epsilon 0 and epsilon 1. Then P, as you can see, you have only two energy levels, epsilon 0 and epsilon 1, right? So N1 by N. So if you have N1, that is coming to so total number of particles is N, okay, where N1 particles are going to epsilon 0, right, and N2 particles go to, say, epsilon 1. Now first of all, the partition function, the summation, will have only two terms, right, which corresponds to epsilon 0 and epsilon 1, right? So this is for a two-state system. Now if you have that, you know how N1 is related to the total number of particles and N2 is related to the total number of particles if you know P, right, where P is given by this, right, which is basically the same as ZMC. Now once you know that, you can use the Helmholtz. So if once you know that, you know the F is minus n kBt ln P, right, and P is the partition function here, grand canonical partition function. Now if you take epsilon 0 is epsilon and epsilon 1 is 2 epsilon, basically you can use that and you can get into very useful relations. For example, just by knowing the partition function, knowing the energy levels, so knowing the particle based description, we can basically get, right, see, we just have a particle based description or atomistic description, and just based on the description, because there are two energy levels, we can easily get back the Helmholtz free energy, internal energy, entropy, and CV, and so on. So for example, this is something that you can prove, right? You can prove in this two-state system, not two particle. Remember, particles is n, but the energy levels, there are only two energy levels that are available. Now if the energy levels are like one is epsilon, the other is 2 epsilon, then basically you can prove that CV equals to, so basically epsilon 0 here, epsilon 0 equal to epsilon and epsilon 1, there are two. So it's again for a two-state system, for a two-state system. Two-state means it has two energy levels and one is epsilon and the other is 2 epsilon. Then you can basically prove that, right? So this is something you can think of doing by yourself to understand exactly all the concepts. Monoatomic gas, we know, for example, argon, neon, so these are all monoatomic gases, and they you have, say, for example, for one particle state, if you have to define for one particle, then you have to give its mass, right? For one particle, you have to specify the mass and the positions, the position coordinates and the velocity coordinates. If you give mass and velocity coordinates, basically you give the momentum coordinates. So you have m, vx, m, vy, m, vz are the three momentum, right? The three momentum coordinates along x, y, and z, and you have also this x, y, and z, right? These are the position coordinates. Now, once you have that, you can basically write the energy for one particle is half mv square, which is half mvx square plus vy square plus vz square. Okay, so this is for one particle. Now you can think of the gas as in a container Lx, Ly and Lz is at the dimensions of the container, but the velocity can go anywhere between minus infinity and plus infinity. Right? Vy also can go anywhere between minus infinity and plus infinity as long as it is finite. And again Vz also is that. So then if I want to establish a partition function, it is for canonical. So this is the canonical partition function, right? ZMC or P. Then basically, right, this is a canonical partition function. It the power minus epsilon by kbt, right? And but you have these integrals. Now you have dvx, so because there are 6 variables, right? Dvx, dvy, dvz, dx, dy, dz, right? So now if I do this, so you have, say for example, you have so the dimensions are Lx, Ly, Lz, but the velocities can go from minus infinity to infinity, minus infinity to infinity, and minus infinity to infinity, right? But the dimensions are from 0 to Lx, 0 to Ly, and 0 to Lz. This is the partition function, and here what are the energies? We know for one particle, one energy is minus mvx square by 2 kbt, and then minus mvy, so basically half mvy square, half, right? And you have epsilon by kbt, and epsilon, as we know, is half mv square, which is this, right? So again, we are not considering any other interaction energy, so we are just considering that. So this is for a monoatomic, and you can see we can think of this as a let us continue, then you will see what it is. So basically you are looking at only the translational kinetic energy, right? So if I do this, what I get is e to the power minus mvx square by 2 kbt dvx, and this is dvx, this is dvy, this is dvz, and this part of the integral is nothing but the volume, right? It is Lx times Ly times Lz, right? Which is basically the volume of the container, right, in which the gas is enclosed. Now this part is the interesting integral, where the integral goes from minus infinity to infinity. It's an infinite integral, right, with the limits at minus infinity and infinity. Now if you see, if you try to, so this is called a Gaussian integral, right? You have seen the Gaussian functions, normal functions. So you have like e to the power minus ax square dx, the minus infinity to infinity, the answer is root pi by a, right? A is the coefficient. Now here the coefficient a is nothing but m by 2 kbt. So minus e to the power minus mvx square by 2 kbt dvx is nothing but root over of 2 pi kbt by m. So the partition function becomes v times 2 pi kbt by m, right, root over, and then again this is for the x component, then for the y component as well as for the z component. So you get 2 pi kbt by m to the power 3 by 2, right? 2 pi kbt m to the power 3 by 2. So basically now if I have this expression, I can take logarithm on both sides. I get ln p equals to ln partition function equals to, or logarithm of the partition function equals to logarithm of volume plus 3 by 2 ln 2 pi kb by m plus 3 by 2 ln p, right? So now we can basically write u, which is basically n kbt del ln partition function del t, right? We have proved this already. So which is basically n kbt square into 3 by 2 1 by t, so it becomes 3 by 2 n kbt or 3 by 2. So or 3 by 2 you can write, if n is a Avogadro number, 3 by 2 rt, right? And this becomes am I correct? 3 u is, you please check this. I think what we have done is correct. So 3 by 2 rt. So and CV then is basically nothing but 3 by 2 r, right? So if I have u get t square and there is a t, so t and t square cancel, so you get 3 by 2 nkb. So 3 by 2 nkbt or 3 by 2 rt, and CV is 3 by 2 r. Yeah, so you please have a look at this, and so this is in crux, and it can be applied in many places. Again, for Langmuir and absorption isotherm, when I discuss that, I will again bring back these concepts of the statistical concepts and statistical thermodynamic concepts, and we will use these concepts to for deriving many useful relations which describe the fundamental properties or thermodynamic properties of materials, whether it's a polymer or whether it's a say for example particles getting absorbed on a surface. So all places you can basically use this connection. And what we have established here, and in very simple terms and very rudimentary way, is this is not a course on statistical mechanics, but it at least gives you the idea how you can relate the macroscopic or phenomenological thermodynamic quantities with the particle based description. And as you can see, we derived these partition functions, we understood what these partition functions are, and we have used this, and we have seen that this basically gives you the same results that you obtained in macroscopic thermodynamics, right? So with that, again, the same thing, you please pass on comments. There may be some places where I have gone too fast, so wherever there is some doubt, you can basically give me these comments. I can try to work on them and try to explain all these concepts. Thank you so much. Thanks.